So this last section of 3.4, we're talking about the sum and product of roots. And admittedly, I'm still working on an explanation for kind of why this matters and where it's coming from. But it's still an interesting thing we can look at nonetheless. And maybe actually if it's something that you're interested in, you can look at it for your IA or your extended essay and explore kind of the significance and the importance of these and maybe even apply it to different types of functions or classes of functions. So, but before we do this, I want to look at some different types of notation that we're going to see because this part of the chapter, this part of the section is very notation heavy. And it is really easy to get lost in the notation here. It's more that we're going to see in chapter 1, which is actually the chapter that we're heading to next. So this is, I guess, is kind of a preview. We kind of do it backwards, right? Because we haven't done chapter 1 yet, where the book kind of expects you to have seen this already. Where this time we're actually previewing it now and you'll be used to it when we come to chapter 1. So the first thing we have is sigma notation, and it looks like this. So kind of an example, maybe to look like this. Right, so we have a whole bunch of different parts here. Maybe I'll actually blow it up a little bit over here so I can mark it up better. We have what we call the index, and that's why we use I. So it's also one thing that makes it a little bit tricky is you see I a lot for index here, but it doesn't mean the complex number. So maybe I'll use K just to try to be a little less confusing. So we have K for our index this time. We have our lower bound. We have our upper bound. And we have what is effectively our function. We have, I guess I'll call it our function for lack of a better term. But this is the term that we're dealing with and we're evaluating at each term. And sigma indicates a sum, right? So I remember S sigma sum. And all this is going to say, this example is to say, well, my function is just the number I'm on. So every term I have is just going to be that number term, right? So when I is 1, when my index is 1, my whole output, I guess, is 1. And then when it's 2, it's 2, and 3, and 4, and 5. And because it's sigma, it's a sum notation, it's a summation notation, I'm just going to add up all my terms, and I get 15. We could do this with 2i, we could do this with I squared, right? If I did it with I squared, my second term would now be 4, and then 9, and 16, and 25, right? And I would just add them all together because it's a summation. Well, we also have the same type of thing for a product, and we use a capital letter pi for that instead of a lowercase pi that we use for, like, normal things with pi. So again, we'll just kind of do an example. Maybe I'll do 2i for my example this time just to show you. So my first term is going to be 2 times 1, and then my second term is going to be 2 times 2, and 2 times 3, and 2 times 4, and 2 times 5. And then I would just multiply those all together, so I get, oh geez, all right, I get 8 times 6 is 48, times 8 is 32, 3,840, I think. I kind of just put myself on the spot there by mistake. But you're going to just see this notation. You're not necessarily going to be asked to compute with it right now, but you do need to be familiar with what it's saying because we have a theorem about it. So given a polynomial, and again, here comes my general notation again. So just my polynomial with real coefficients and a leading coefficient that is not 0. Right, so remember this just means real coefficients. And I have zeros, x sub 1, x sub 2, x sub n for as many zeros that I have degree, right? Then I can actually look at the sum of all those roots and the product of all those roots. Well, if I look at the sum of all the roots, right, and again, this is what my notation means, right? The sum from root number 1 to root number n, and again, that just means I'm adding up my roots, right? So this would just look like root number 1 plus root number 2 plus root number 3 plus 4 plus 5 plus da 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 all the way to n. I get negative a sub n minus 1 over a sub n, and you're like, what the hell does that mean? I can hear you all panicking already. It's not that bad. A sub n, well, we see a sub n, right? A sub n is right here. A sub n is just my leading coefficient, which is one of the reasons that my leading coefficient cannot be 0. And this is the coefficient of the n minus 1th or n minus 1st. It's always an awkward thing to say in math. Term. Right, so if I have a polynomial that's like 3x squared plus 4x minus 5, then here would be, my leading coefficient would be a sub 2, right, because it's the highest degree. I guess that's not a sub 2, is it? This is a sub 2. And then a sub n minus 1, well, 2 minus 1 is 1, right? So here is a sub n minus 1, 2 minus 1, 1. Right, if I had like 20, I'd be looking at a sub 20 and a sub 19. It's not necessarily just the next term in the polynomial, it's the one of the degree 1 lower, which may not always be there, and you'll see that in a second. If I have a product, it does mean all kind of the same type of thing, right? So, except it's multiplication, so it's 0 number 1 times 0 number 2 times ... all the way up to 0 number n. And it works like this, and it's a little more complicated looking. So negative 1 to the n, and n is just the degree, a sub 0 over a sub n. Well, let's break this down too. A sub 0 is just the constant, right? There it is, right here. A sub n, again, is just the leading coefficient. And this negative 1 to the n is interesting. This negative 1 to the n is going to show up quite a bit when we talk about sequences in chapter 1. N is just the degree. Well, what this tells us, kind of what an important result of this is to say that my product of roots here will be positive if n is even and negative if n is odd. So that's just something to pay attention to. It's something we call, I believe, parity. Is parity even and odd, or is it positive, negative? Don't take my word on parity. I'll come back to that in chapter 1. But it is something that we do see quite a bit. Maybe I'll try to edit that into the video just to get a good definition on parity since I brought it up. But let's go on to some examples for now. So I want to find the sum and product of the zeros of just the following polynomials here. So let's talk about the sum first. So the sum of my polynomials, we're going to use my sum formula. So I like to write it in general first, and then I'll plug in. So my degree is 4, right? My highest power here is 4. So a sub 4. And then n minus 1. So if n is 4, n minus 1 is 3. So I'm looking for the degree, sorry, the coefficient on the 4th degree term, which is 1. And I'm looking for the coefficient on the 3rd degree term, which is 3. And it's negative, because negative is built into the formula. So the sum of my roots is negative 3. The product of my roots, which feels like maybe some weird like genealogical thing. I am the product of my roots. Sorry, that was weird. Here's my formula right here. Well, degree is 4. So I'm just going to plug those in, right? Well, even power, negative number to an even power is positive, such as positive 1. My constant, use a different color here. My constant is negative 2. And again, my leading coefficient back over here is 1. So the product of my roots is negative 2. That's all we're doing. It's just plugging into the formula, right? The process itself is not difficult. The challenge in this problem is understanding the notation, especially with a problem like this, right? This has all been set up with notation. The process itself is not complicated. My degree is 2019. Right, so 1 minus that, or sorry, that minus 1 goes on top, 2018. So the coefficient attached to my degree 2019 term is -5. I want to look at the coefficient that's attached to my 2018th power term. Well, it's not present in my function, which means that it's a 0. So the sum of my roots is 0. And this actually is a thing that we notice pretty frequently, is when there's a term missing, right? When that second term is missing, the sum of the roots is 0. Let's take a look at a product. So I've got -1 to the n, 0 over a to the n. Again, my degree is 2019, so I'm going to write that in, whoops, a to the 2019, or sub 2019. So negative number to an odd power stays negative, so -1. Leading coefficient, sorry, constant is 21. Leading coefficient is -5. The negatives cancel out. The product of my roots, 21 over 5. That's all we're doing. In the context, the curriculum doesn't want you to go any further with it. It just wants you to be able to compute the sum and product. We'll see maybe a slightly more tricky form of the question, but you're still not really doing anything beyond using the formula.